A Nephilim spider joining the monsoon banquet. She's caught a tiger butterfly. And he is utterly toxic. Butterfly predators need to learn this.
System error. Shutting down.
Walk, don't run. Use the handrails. Walk, don't run. Use the handrails.
Neon Temple simulation reboot in progress. Live stream initiated. Stabilizing environment.
everybody. Another week, another guild night. I am not going to stand here and run my face forever because we've got a really cool topic and a really cool presenter, so I'm going to get out of the way. Quick cliff notes. Prepper month starts next week. John's got a cool going over preparedness in general, making sure you know what you have in your house, what you need, all of that kind of fun stuff. And I believe starting this weekend is the BJ's run if you need to go stock up on bulk food items, toilet paper, that kind of fun stuff. So if any of that is of interest to you, let him know. There'll be an announcement later on this week, or I guess tomorrow, because it's Thursday, in announcements about how it's all going to go down and what's moving on to the future. From there, we're doing Prepper Month stuff. We're getting ready for the 502 summer camp. If you want to help, if you want to volunteer, it's a really cool program we do with USF and the 502 project. We do it every year. Let us know. Let one of the leadership know, or Fake Jay, Bosch, whoever else is involved, if you have interest. Ask them how they thought it went. The dates are, I want to say, the week of the 22nd of July. So end of the month. Sounds about right. Yeah. So that's coming up. Yeah, Prepper Month. So with all that being said, DM here has an awesome, cool little how to build shellcode hands-on workshop / talk going on for us, and I'm excited to see this one. So I'm getting out of the way.
Cool. All right, guys, we're going to jump right in. We got a lot of content here. So just so you guys kind of have a little idea, this is going to be probably about 1/3 lecture and 2/3 workshop. So we'll jump back and forth. For those of you, real quickly, I realize I probably should have put this on a slide because I didn't think about it in the beginning, but if you're having trouble, if you weren't in our Discord and didn't get the kind of pre-announcement thing, you can download the repo that we're going to be using. If you search my name, disc0rdantmel0dy, the O's are zeros, and GitHub, you'll see my GitHub. The repo is called Krabby Patty. You'll want to pull. If you're wanting to follow along, you can pull that down. There's instructions for setting up Visual Studio as well as the code that we're going to use today. If not, if you don't get to do it today with us live, that's fine. I did include a documented, a very overly documented set of code there that will cover a lot of what we're talking about. So you can, so you should be able to go back and build your own rudder based on that afterwards as well. So jumping right in, yes, I'm a consultant. So yes, I have an agenda slide. So we're gonna do some introductions. I'm gonna talk a little bit about what a shellcode loader is. Then we're gonna talk about some Windows API calls within the C#.NET framework. And then we're gonna go through, do a couple of back and forth between lecture and demo to actually build a simple shellcode loader. And then we'll wrap up with some questions. So before we get started, I have a bad habit of using some terms interchangeably, so I just wanted to kind of let you guys know that if you hear me use the term implant or the term rat, those are I will use those interchangeably. Same thing with shellcode loader and shellcode runner. That one's technically, we usually refer to them as loaders these days because it's what they actually are. But shellcode runner is kind of the old terminology that a lot of hackers use to describe what we're doing. So I may use those a little interchangeably. So a little trigger warning here. Following hour, you're going to be exposed to some bad humor and possibly some bad language. I will try to keep it clean, but my language on a good day is saltier than a pirate. So just be warned, I may use a few bad words. We're all adults here, it's fine. The second thing is you're also going to get exposed to a lot of code. Shellcode running is a programming sport, so yeah, we're going to be doing code. Also, I know Windows is kind of a dirty word for a lot of hackers, but we're going to be using a lot of Windows here. And the primary reason for that is that all of the so the loaders that we're going to be working on today are designed to operate in a Windows environment, so they're meant to be your target. Also, Windows gives us access to Visual Studio, and Visual Studio makes coding in C# very, very easily. And then, yeah, there's going to be enough SpongeBob to make your eyes bleed. All right, so who am I? Why do you care? My name is disc0rdantmel0dy, also known as Chris Russell. I am a bit of a PowerShell and C# nerd. Big note here is I am not a real developer. So, you know, if I have some developer come over here and start complaining about my code etiquette in C# and my assembly design, I will probably throw something at you, so you've been warned. I do love to do malware development. Malware development is functional. It's not necessarily pretty. And I run the offensive operations group over at Fulcrum. So let's just get right into it. Like, what is a shellcode loader? Actually, before I start putting the bullets up on the slide, can anyone here tell me the difference between shellcode and a shellcode loader?
One does the thing, the other loads the thing.
Not a bad way. So a shellcode loader is it's a wrapper program. It's a shellcode loader executes shellcode. Shellcode can't be called on its own because since what shellcode actually is the raw bytes that will end up in memory that have the instructions for the shellcode. It's not meant to be, and it's meant to be executed directly from a process's memory space, not by itself. So it's only executed if you can copy it into memory somewhere and move the execution pointer to the beginning of it. So just to kind of reiterate, so what shellcode specifically is, it's low-level byte code that carries a specified set of instructions. It's usually used to load a remote access tool or an implant, or possibly just execute a pre-built set of commands. The things to note here that shellcode is not a fully functional program, and it's not something you can execute. If you pull down shellcode out of Metasploit or out of Havoc or whatever C2M, and you load that shellcode and you double click on it, nothing will happen. So in order to execute shellcode, our loaders have to do 4 things. First thing they have to do is they have to import the shellcode representation into a byte array. So when you get shellcode out of a C2 program or you pull it off of ExploitDB or any other number of places you might get shiesty shellcode from, it is generally in a string format. And that format is not able to be interpreted by the computer. So, it's really meant for us to be able to interpret what bytes are there. So we have to convert that into a byte array inside our program. We'll touch a bit on storage in a bit, but the main thing to know here is you got to make sure you get it into that actual computer array of bytes. The second thing we have to do is we have to allocate memory inside a process. That could be a local process, like our own loaders process space, or it can also be in a remote process. Today, the one we're going to work on is going to be allocating memory locally. And it is important to note that you do need to allocate the right amount of memory, because if you don't allocate enough, then the program kind of just craps the bed and doesn't execute. If you allocate too much, you may have issues with stability inside your program, because what happens is when you allocate that memory is not zeroed out by the OS. So there are instructions that were in that memory space previously. So if you allocate too much and then you just throw your shellcode in there, it'll run, but then when it gets to the end of your shellcode, instead of finishing and doing what it's supposed to do, it's going to try to execute those other invalid instructions. So in some cases, it'll work, and then in other cases, it will crash. So we want to make sure we allocate the right amount. The third step that we have to perform is we have to copy our shellcode, that array of bytes, into the allocated memory region. That's pretty self-explanatory, so I'm not going to dive too into much there. And then the last thing we have to do is we have to set EIP, or the execution instruction pointer, to the beginning of our shellcode. EIP is just a really fancy computer science way of saying the next line of code to execute. Everything else that you might see in some like, if you've ever looked over the code of shellcode loaders, some of these things are thousands of lines. I know that the loader that I designed internally for live ops is about 2,000 lines long. Everything else outside of those 4 steps is just evasion. So let's talk about how we're going to do those things. So to perform those functions, we're going to need to leverage Windows API calls. And that API call is simply a function that's provided by the OS to accomplish a task. It's usually in a DLL file in Windows. There are some built-in Windows APIs as well that aren't stored specifically in DLLs, but we're not going to talk about those. It's important to note that you can only call a Windows API call from inside of a program. This isn't something you can just type into the command line or something like that. You actually do have to write a program to do it. So before we dive too much into the Windows API calls, I want to do a quick overview of managed versus unmanaged code. So in C# and the .NET framework specifically, what makes the .NET framework do what it does is it's built up to this concept called managed code. And these are built-in functions inside of the .NET framework that allow you to do different things. So basically, they took the most common API calls that people needed to write programs, and they keep bundling them into the .NET framework. They're kind of easy to use, so they tend to be very short. It takes very little code to actually get those functions to run. And they're imported into the program with the using command. But they also rely on the target system has to have the correct version of the .NET framework installed. We are going to use a managed function in this loader, but we're also going to use some unmanaged code. Unmanaged code is basically everything else. So if it's not built into the .NET framework, the .NET framework will allow you to import those functions into your code and allow you to still call them. The downfall is they're usually complicated. There's more lines of code involved. You have to do an import of the function. You have to declare it, and then you actually usually have to call it with the full API syntax. They're usually imported from an external source like a DLL file, and then each function that you're importing from a DLL has to be imported separately. You can't just say import this DLL. You actually have to import each function individually. Make sure I don't miss anything here. All right, I'm going to attempt to give you guys a kind of quick overview of Windows internals. This is a really large, complicated subject. And if you continue down your maldev journey here, this will be something you become intimately familiar with. But I want to kind of give you guys the overview so you guys can understand what's going on as we start breaking into Visual Studio and writing some code. So all OSs really, but Windows specifically, since we're talking about that, is basically divided into 2 logical spaces. You have the user land and kernel land. User land is, or user land and the kernel. User land is usually what you think of when you think of an OS. So that GUI that pops up and you hit start, run, and all those fun stuff, that's all user space. Also, any application that's executed by a user, which really can be read as any application that is not a direct Windows internal application, also executes in user land. Then you have the kernel, and this is where all the OS internal stuff happens. So when you run an application, the application says, hey, do this. Underneath the covers, the OS has to allocate memory, it has to do all these different things, and that all happens in the kernel. So the security rules of the OS state that if you're coming from user land, you can't communicate with the kernel. And this is by design, and it's built into the architecture of the OS. Technically, there's kind of a third spot in Windows, a third layer called that I usually call the traversal layer, and this is not the kernel because you can still talk to the traversal layer, but it's only supposed to be being used by the OS. So if we're doing writing applications, things like that, we need to get the kernel to do things. Otherwise nothing happens. That's where the processor is. That's where the memory is. Everything. So the way Windows expects you to do this is by using Windows API calls. Generally, the ones that are built into kernel 32.dll. That API call then communicates to that traversal space, which usually calls a lower level API called ntdll. And inside that ntdll is where all the API calls that actually talk to the kernel. We can call ntdll directly. We're not going to do that here. It's actually really important as you start getting into EDR and AV evasion, because the big thing to note that though is for this topic is that if you call something in kernel 32, all it's going to do is call ntdll. It's going to make a more complicated call down traveling deeper. The big thing is here, Windows only supports applications interacting with the kernel through the kernel DLL. All of ntdll is undocumented. Microsoft doesn't expose any of that to us and tell us what it is. However, over the years, hackers and developers have reverse engineered the heck out of ntdll, and you can actually find nearly good documentation for nearly all the functions. Generally, when you're getting into more advanced shellcode, or shellcode loaders, you will be using the kernel or the ntdll. But for starters, we're just going to use kernels today. All right, so a lot of what we're doing when we developed shellcode is reading API documentation. All of the APIs that we're going to use, which I'm going to go through here, we're going to have to read some documentation. All of the Windows or Microsoft officially documented APIs are at something called, or they used to be called TechNet. I think they just call it Learn now. But I'm going to pause on the presentation here for a second. I'm going to show you guys one that we're going to look at here. So wait for single. There we go. All right, let me toss this over to. All right. So this is TechNet. This is actually an API call that we're going to be using in our loader. The key things I want you to kind of get used to seeing here is all of the API calls that we're going to use, the documentation is set up in the same way. It's going to start with syntax. You do need to be careful here because some of the Windows API call documentation is going to be like this one, where the syntax is shown in C or in C++, and some of it will be in inside, or it'll show you the syntax in C#. If it's in C++, you're going to have to make some conversions because the types, which are these little like keywords in the beginning, these are different in C++ and C#. So you'll have to go do a little research and go, okay, what is a D-word type from C++ to C#? So you'll have to fix those up a little. All the parameters are explained. This is a pretty simple one. It only has 2 parameters. And this is a bad example for this, but it'll also tell you how the function returns. So generally, you have 2 types of functions. You have ones that return stuff and ones that just do things. In programmer speak, that's you have voids and returns. This is a void, so this one doesn't actually return anything. But if it does have a return, you do have to give your program has to have a place to store that return. Otherwise, the function will fail. And we're going to look at a lot more of these here in a bit. I just kind of wanted to give you guys a quick. Oh, I lost my cursor. There we go. All right. Yeah, so the big thing to be aware is just make sure you're looking at it carefully at your documentation to see that the syntax is in the right format. I have definitely had some problems tracking down bugs due to that. All right. So the first step that we talked about happens all inside the program. So we're going to skip that for now and come back to it. But let's talk about the API calls that it's going to take for us to actually do the 4 steps that we talked about earlier. So step 2, we have to allocate memory. So the easiest API call to use for this, there are many, and you should learn different alternatives because like virtual alloc and virtual alloc EX are big targets by EDR vendors to try to, so if you actually start trying to write evasive loaders, you need to find alternate ways to accomplish things. But virtual alloc is the quote-unquote right way to allocate memory in Windows. So it basically just requires 4 parameters. The first one that it is the base address. So base address is a technical way of saying we want the memory address of the first byte in our allocation. So what that means is essentially if you're looking at your array of memory that you're trying to allocate, it will be the array at index 0. So basically the very, very beginning, first byte. Not generally you will get that from somewhere else, or you will set it to 0. And in our case, we're going to set that to 0 in most of our loaders because it's very rare that you actually need to allocate memory that when you're going to put your stuff in it, it doesn't start at 0. The second thing that we need to allow it is the size of the allocation. So this is kind of the big one. This is the one that will cause this API to fail. I kind of talked about it earlier. If you don't allocate enough, bad things happen. If you allocate too much, bad things happen. So when we get into the code section here in just a minute, you'll see that we're gonna allocate this dynamically in our shellcode runner. So that way, no matter what size we put shellcode in, the API calls, it's going to check that size and go back to it. The third one is the type of allocation. There are a whole lot of memory allocation types you can do. Off the top of my head, I can think of 6. For purposes of our talk, in shellcode loading, you're almost always going to use mem commit. What this means is that when you're telling the OS that when you allocate this memory is already earmarked for something. So it won't ever try to put anything else in that memory space until you free that memory. And then the last one here is another one that gets people in trouble, the memory protection mask. So when you allocate memory, you have to tell, just like everything else, you have to give it permissions. In our case, we're going to give it read, write, and execute permissions. That's usually not a good idea. Generally, the moment you put read, write, execute permissions in your memory, on your process memory, the AV and EDR will tell you to go screw yourself. However, it is easy, and that's one of the reasons we're going to do that today. What this means is that memory space, we can write to it, we can read from it, and we can execute. Generally, real programs, you're going to make memory like read, write. When you need to write to it, and then you're going to change the memory permissions to read, execute when you no longer need to modify the memory. There is an API call that virtual protect and virtual protect EX. That API call is what allows you to change that afterwards. In our case, we're not going to mess with virtual protect because we're just going to give it full permissions the whole way. This, one last thing before I move on from virtual alloc. Virtual alloc does have it is a returning API call. So when you call virtual alloc, it will return a pointer that points at the memory space you just allocated. So we are going to have to save that in order for the API call to run, but we're also going to need that for our other API calls as well. When we start getting into the actual loader portion of this, you'll see like almost all of our API calls feed one into another very easily. So after we've allocated that memory, we've got to copy our shellcode into it. So this is a managed API call, so it's inside the .NET framework. It also requires 4 parameters. The big things here is your first parameter is your source. So that is whatever variable you saved your shellcode in. The second one is a start index. it's almost always, again, like I said earlier, from the allocation, it's almost always going to be 0 unless you're doing some weird shenanigans. The third one is the pointer to the memory destination. So for those of you guys who aren't big into CS and programming, a pointer is basically just, it's an address that contains the memory address of the object. So it does what it says on the tin. It points to a specific spot. That is the pointer that comes out of virtual alloc that we talked about a minute ago. And then the last, you'll notice in programming, we do this all the time when we're dealing with memory. It will always, anytime you're touching memory, you have to tell it how much memory you're touching. So we'll dynamically generate that from the code. And that's going to lead us into our first demo. Anyone who's going to be following on, was everyone able to get Visual Studio and get the repo downloaded? Cool. All right, we're going to jump right in then. So
If you didn't get the repo, it's inside the announcements channel. You can see it there.
Oh. All right. Come on. You get my VM over onto the screen you can see. All right, so for those of you who are following along, we're going to be working in the Krabby Patty demo project. There's 3 projects inside that solution. 2 of them are meant for more like just being able to review, and they're functional mostly. There might be a couple of bugs in there, but we're going to be working inside this Krabby Patty demo. All I've done here is, there we go, is I have created a new project. This is just how, if you create a .NET C# console project, outside of all the green text that's in here, let me see if I can make this a little bigger. Outside of the green comments that are in here, this is what will get pushed out from just for a starter project. Let's see, view, can we make this bigger? Okay, I was going to try to make this bigger, but it doesn't look like it's going to let me inside the VM. All right, so the first thing we need to do, one of the early things we talked about was importing managed code with the using command. So it will always throw all of these various usings in here. We don't actually need these, so we're going to get rid of all these guys. So the first thing we're going to add is we need the managed code that allows us to do marshal.copy. So that exists inside the it exists inside the system, which we're already using, but it's actually specifically in system. What is it? System.runtime.interrupt services. There we go. And VS makes it very easy to just tab complete through this. The reason we're going to declare this, even though we've already declared system, is by declaring it this namespace. The namespaces are basically the entirety of like what makes the .NET framework the .NET framework. Normally, if I wanted to call something out of interrupt services, if I just loaded system, I would have to type, every time I want to do it, I'd have to type system.runtime.interrupt services whatever function I want to call. By loading this separately, I can actually just call the function. The next thing is we need to actually load our DLL, the unmanaged code from our DLLs. I don't want to get too deep into like namespaces, but just so you know, generally in a .NET assembly, you will load your externals inside your class namespace, but outside of your main function. So, for practical purposes in our space, we got our namespace, which is our actual program name. We have a class because all .NET assemblies are DLLs that are automatically injected into themselves. Don't ask, it's weird. I don't know why Windows does that. But inside of our class, that's where we're going to deploy this. So the first thing we need to do is we need to load the virtual alloc. And we'll do that with the DLL import keyword. So the way we do the DLL import, sorry, this is really small on my side. So we'll call DLL import, let it populate. Then DLL import is a function. So in functions in C# always have the function name, and then everything is inside parentheses. So we've done DLL import, so then we're going to go, we're going to do the location of the DLL. So for Windows internal DLLs, so basically anything that exists inside System32, we can call those directly without having to put the path. So we're just going to do kernel, oh, that is 32, not 42, .dll. And because it's a string that we're processing, it'll be inside of quotes. And then we're gonna then that gets closed. Both of those get closed. And then the next line after that, so we've told it where to import from. Now we have to tell what we want to import. So in this case, we're gonna make it private because everything has to be declared with a scope for if you're keeping everything in one file, you can make everything private. It doesn't matter. So we're just going to do that for easy. And it looks like VS is trying to write my code for me again. All right. So the second keyword that we have to use, because it's something that we're going to be calling elsewhere, it needs to be static. Static just means that once we've imported it, it doesn't change. And then the last thing is we need to tell it it's an external function. Oops, lost my cursor. There we go. So all of this is just setting up. Like this is C# speak for we're going to import a private function from an external source, and it's not going to change after we import it. So in this case, we just need to do. We're going to do virtual alloc first. So we have to tell it what type it's going to be it's going to return. So we're going to put int pointer. Type. Nope, there's no bracket after the extern. And then we're whenever you declare a new function or variable or anything in C#, you have to tell it, you have to declare the type. It's an explicitly typed language. So we know the return from our documentation that the documentation, which actually, let me pull this guy up real quick. We're going to do virtual alloc. And we'll pull up the TechNet. Got a little ahead of myself there. All right. So again, the syntax is here. This is in C# or C++, so we'll have to convert that. But the main thing I want to look for right off the bat when I'm declaring it is I need to figure out what the return value is. So in this case, it returns the base address of the allocated region of pages. Earlier I said that's just a very fancy way of saying it's a pointer. It's a pointer to the memory space. So if we go back over here, so we declare int pointer, and then we're going to tell it the name. So in this case, it's going to be virtual alloc. And then we need to do since it's a function, we're going to put our open and close parentheses. So then we basically need to go back and copy parameters. Where did it go? Come on, come back. I have too many displays and there we go. We need to go back over here into the syntax and we need to capture all these parameters. Because these parameters that are in here, let me scroll that up to the top a little. Those parameters have to be in the API call for that API call to work. So I know that I need the LP address, DW size, all of these ones that have types next to them. These types are in C++, so we're gonna have to convert those. They're converting types from one language to another is a little bit, it's a little science, a little art, because you generally have to get something that's close enough the OS will recognize, but there's not always a one-for-one. A great example of that is size t is technically, it's the closest thing is what we would call an unsigned integer, but it's not really in C++, it's not really an unsigned integer. So sometimes you're gonna have to go maybe do a little experimentation and see if it compiles and if it works. You spend a lot of time in Stack Overflow when you type in, how do I convert X to Y, and you'll usually find someone who's got the right answer. In this case, in the demo file, I did every time that I put these in there, I did put both the C++ and the C# types to make it a little easier. Little cheat code here. Generally, if you get a weird type in C++, it's probably an unsigned 32-bit integer. So if you can't find anything, try uint32. That will work about 90% of the time, unless it's a pointer. Pointers are almost, there's only one type of pointer in C#, and that's int pointer. So if you see it that's describing a pointer, use int pointer. uint32 is usually a good guess too for the next one. All right, so in this case, I have these ones listed on my little cheat sheet here so I didn't have to flip back and forth. So the first one that we're going to do is the I keep losing my cursor here. So it's going to be the LP start address. You don't have to name, you can name these whatever you want because the name doesn't matter when it goes to the OS. So sometimes I will change some of the names to make them a little more easy for my brain to understand. But again, because well, you're not going to let me type? Come on. There we go. Get back into VS. All right. So we're going to do int pointer, because we know the first one is a pointer from the documentation. So then we're just going to do, we're going to do an LP start a DDR, add a comma, and then we add our next one. Next one is the size. So I'm actually just going to call this size. Again, this one particularly converts into uint32 as the closest thing. And it did, oh, I guess it helps if I actually type uint correctly. If you look when you start typing it, you will see there are a few different ones. Make sure uint32 is each one is a different format. So make sure you have, when you're looking at, if you just see uint or something like that, make sure you actually read in whatever article to find out whether it's a 32 or 64-bit. Like I said, most cases in C++ to C#, it'll be 32-bit unsigned integer. So that second one is the size. So we'll just call it size. And then our third parameter is it's going to be another uint32. And that one is our allocation type. And I'm just using these particular names because I'm going to show you guys some of this. Some of this I'll copy and paste so it doesn't take so long. So I'm trying to make sure I get all of the expected parameters that I had them named at in my paste pad here. You know, I'll give you one free one because you weren't here when I threatened to throw something at anybody who like insulted my coding practices. So that was your freebie, Crispy.
He's just being himself.
That's true. We wouldn't know it was him otherwise. All right. So the last parameter that we're going to put in for this guy is going to be our memory protection mask. So again, it's another UN32. Like I said, you'll find that you'll be typing that type a lot. And I'm just going to call it FL protect. And then another little like C# thing. Well, it's a lot of languages, but not necessarily all of them. All lines have to be ended when you end a line of code. And mind you, what we did first with the DLL import, this is all considered one line of code. I know that even though it's on 2 lines, but when you end a statement in in C#, you do have to close it with a semicolon. Don't worry, you'll never be able to miss it because Visual Studio will yell at you 10 ways from Sunday if you forget a semicolon, and it won't compile. All right, so now I'm going to cheat and copy the other 3 so we don't have to go through that again. I just kind of wanted you to see how an API call is put in. I'm going to copy. So let's grab. So all we're going to end up doing is doing the same thing. We're going to look at the syntax in the API call documentation, and then we're going to transpose that into our program. So let's copy. And we're going to put this in here, and then we'll move on to the next part. All right. So now we've imported our API calls. So now they're ready to be used in our program. I am going to put a placeholder in for the shellcode because we haven't actually talked about how we're going to do that in this one. So we're just going to declare it. So we know it's going to be a byte array. So we'll set the type to byte, and then we'll do an open and close square bracket. That tells the compiler that it's an array. So that now that we set the type, then we're going to go ahead and do new. What did I name this in the code? Sorry, there we go. Okay. I guess I named it something different in the final version. So after we declare the type, we give it a name. So I'm going to call it new shellcode bytes. And then so this is a variable. So when we declare that, we'll just add in equals to say what it's going to equal. And in this case, I'm just going to do an open and close bracket for now as a placeholder. We will put that in later. And then we'll close that with a semicolon. I'm just doing this now because when we start writing the API calls, since we're going to dynamically check how long that is, we need that variable declared in order to check the length. Otherwise, the other code, when we start writing this next part, it's going to get Visual Studio is going to complain about this object not existing that we're calling. All right. So Virtual Alloc, we talked earlier on the slide that we were showing the API calls. We talked about a couple of the parameters, like the allocation type being having mem commit. That's actually a hex entry. What I usually like to do for these is I will actually declare a variable. So I will do, since it is a unsigned integer, so I'll do uint32, Come on. There we go. uint32, and I'm just going to call it directly what it's called here. The reason I do this is, one, it makes sure that I don't that when I'm looking at my API call, I know because I think so this one. Let me finish writing this one. So this uint32 is 0x1000. If I look at that in an API call, I'm going to have no idea what that means when I'm trying to read it. However, now because I declared that, instead of typing that, I could actually type mem commit as that part. So then when I'm reading the API call, I know what I'm referencing. So I'm going to do the same thing for the memory permissions. It's also a uint. And then we're going to do, I'm actually just going to copy this because I don't want to type all that out. Nope, nope, come back. Fine. And then we're going to make that equals. So this is going to be 0x40. And on that documentation page, if we go back to it, you can see when we this is virtual Alex. So if we scroll down here, so we can see the mem commit is 0x1000, and I just put it in shorthand. You could do either. That 0x1000 will get converted into that because we said it's a uint32. And then same thing for the memory permissions. When we get into FL Protect, you can see that there's a link here to the memory protection constants. And right here's that list of all those various memory permissions. So in our case, we're doing page execute read write, which is 0x40. And again, these are just there to make it easy to call those in the next step. Before I get into the actual API call, we've done a little bit of code. Does the importing that we did for the unmanaged code, does that make sense? Or did anybody have any questions or want me to stop or revisit anything there? Okay, cool. All right, meat and potato time. This is going to be the first API call that we're going to call. So in the project, I just copied, and I actually do this in my live projects. If I'm doing an API call that's in a different syntax, I copy the whole syntax into a comment. This is just a multi-line comment with that. It just makes it easier for me when I go to start actually typing out the API call. So I'm going to call. So first thing I need to do is I know the output is an int pointer. So I'm going to declare that. And we're going to call, what did I call it inside the code? Int pointer is, okay, so PTR allocated memory. And then I'm going to put equals virtual alloc. I'm going to tab complete that, and then I'm going to put my first parenthesis. So one of the reasons I like the Visual Studio a lot is now because it's going to show me as I'm typing this, like you can actually see what I need to put there, what the types are, whole 9 yards. So again, this time we're going to do int pointer. Whoop. Keep hitting my tilde key. All right, int pointer, and so the first one, just looking at my API call notes. All right, so the first one is the where we want it to start. So in this case, I told you earlier we want to start at the beginning, so it needs to be 0. But this is kind of an interesting thing. So I can't just put 0 here because it's expecting a pointer. So in order to get a 0 that's a pointer, I'm going to have to use a built-in function call called .0. So this equals 0, but it's a pointer to 0 instead of being the actual number 0, because numbers are ints. Second thing we're going to do is so we got our start address, we need our size. So I talked earlier about dynamically generating the size. So when we declare that array of bytes, an array has a property inside it called length. So if you call the array.length, it'll tell you the size of that array. So here, since we're expecting it to be, we're going to do shellcode bytes because that's what we named our array. Dot length, and then we're going to do a comma. And it's going to complain, isn't it? Oh, it won't complain until I finish it. All right, well, we'll get there. So after shellcode bytes, then the next 2 parameters is our allocation type. So we're going to do memcommit. And then our last one is our protection type. So we're going to set that one to page execute read write. And then we'll close it. Right off the bat, we get red underlines on this. And the reason that this is Visual Studio saying it sees something wrong. The reason this is wrong is that and if you highlight over it, it'll even tell you it can't convert int to uint. So we need to actually cast this. And all a cast means is I want you to convert it from one type to another. So I'm going to do, the way we cast is we put an open and closed parentheses in front of it, and then we tell it the type we want to cast to. So now it stopped complaining about our function call. You guys, that makes sense to you guys about casting between? Okay. You'll do this a lot in programming. It's a very easy way. It means we don't have to say, I don't have to declare this variable 5 times in different types. I can just cast it from one type to another. And that's the entire API call for virtual alloc. That will execute and allocate memory. It'll save that pointer in our pointer allocate memory. I'm going to do like I did before. I'm going to copy the other ones in, as opposed to sit there talking through each step by step. Actually, you know what? Yeah, we'll copy it and then I'll just talk through it. So the next thing we're going to need to do is we're going to need to copy our shellcode into that memory space we allocated. So let me copy this in and then I'll talk through this one. Actually, under the comment. All right. All right. So this one is almost, so it's declared almost the same way. The difference here, I did that all in one line. I just broke this out into multi-lines to make it a little easier to comment. Oops. Sorry, I just need to, this is going to bug the hell out of me if I don't fix this now. Are you really not going to let me shit? There we go. Just moving that back in line where it's supposed to be. In C#, because it is a braced language, anything that's inside of a set of any type of brackets, so whether it be square brackets, curly braces, any of those, you can put those on as many lines as you want, so you can make it easy to see. So in this case, we need, for Marshall copy, we need to tell it the source, which is our shellcode bytes. That's that array. We need to tell it where we want to start. In this case, it's 0. It is expecting an integer, so we just put 0 there. The destination is a pointer to an allocated memory space. That's what got generated up here. We saved that output of virtual alloc, so we're going to put that there. And then we're going to call shellcode bytes length again in order to tell it how long. That will copy. So a couple of things to notice since we're using managed code here, the Marshall copy is managed by the framework. It's not we don't have to declare everything with its type and all that stuff. We can just put things in. That's kind of the advantage to using managed code when you can. Unfortunately, in Shellcode Running, you're only going to be able to use managed code for a few things. And I think that is all I had for demo 1. Yep. Now we're going to move back into the slideware for a minute. All right. Let's do. No. Come on. I really need. There we go. Pointer, come back. There we go. All right. We're going to minimize this. All right, so before we move on, did that make sense to everyone? Like, it's pretty straightforward. Like, I find like once you've gotten through and you've written one kind of API call, then it just kind of makes sense. That, you know, put as much documentation in your code you need. Like, I find, like I said, that little thing of just copying my syntax right into there so I can look at it. It's right above the line I'm typing. It makes it really easy to make sure I'm keeping up with everything. All right, so let's go back over here. All right, so let's talk about the last 2 API calls we have to call. So we only have one step left to do, and that is to set the execution pointer. But this one is actually going to take 2 API calls to do. The first one is called create thread. So earlier I said setting EIP is just a fancy CS way of saying, you know, here's where your next instruction is. It can be a little complicated, and this is another one that there's a lot of ways to do. Create thread's just the easiest one. So this is the most complex API call we're going to use in this code, but it's really not that bad because we're not really using it for what it's intended for. We're just using it to set EIP. So move my power here. So what we're going to do is, with this one, what create thread actually does, a thread is the easiest way to kind of think of it is it's like a sub-process. So your process is running. If you create a thread, it's going to go do something else independently and asynchronously. There's not an actual other process generated, but it's just, you know, just kind of way to think of it in your head. What that allows us to do is because we can tell it exactly what we want that little subthread to do, or that subroutine, that allows us to set EIP as part of that. So, and that's actually where the third parameter comes in. This is a pointer to the memory space containing the instructions. By putting that as our memory space we just allocated, that sets EIP to start executing there. The other stuff is actually, in our case, is mostly just filler. So I will explain what they are, so because sometimes you might not actually need these, but in our case right now, because we're not doing any evasion, we don't need to worry about. The first one sets the security attributes of the thread. We're going to set this to 0. In this particular API call, if you go read through all the documentation of it, and this one's a long one because it does a lot of stuff. 0 in most of these things has a special meaning, and you'll find that a lot in your execution style API calls. 0 generally means do whatever you were going to do anyway. So in this case, we want to do the default action for the security attributes, and that default action would be to inherit it from the parent process. So the second one is just describing the stack size. I have never seen this in all of my time programming. I've never seen anybody change the stack size on a sub or on a thread. I honestly don't know how you could do that without crashing the thread. So we're just going to put 0 again and tell it to use the default. Again, the third one is the big one. This is the pointer to our shellcode. The fourth one, again, is going to end up being 0. The thread parameters are basically, so this is another one that's going to be 0, but 0 has a little different meaning here. So the thread parameters are generally things like start suspended, start at high execution priority, or things like that. and it's really taking like, how do you want us to process this thread? But if you just put 0, it just says start it right now, which for us, that's kind of what I want. I want you to run my shellcode right now. And then excuse me, I'm sorry, that's not the thread parameters. That's the thread creation flags. Apologies. Thread parameters are basically like it's a pointer to some security or to some attributes, but instead of being security related, it's more functionally operationally related. Again, we're going to put 0 there too because we just want it to do what it's supposed to do anyway. The last one is a little finicky, and I'm going to explain why. So the thread ID, you can actually assign it a specific thread ID. Every thread in a process has an ID. You probably don't want to do that unless you know 100% that there's not a thread ID already made by that name. Otherwise, you could make both the program and possibly the OS unstable by overwriting the wrong thread. Sometimes we do this in certain evasive techniques, but for the most part, in this case, we're going to set the thread ID to 0, which tells the OS, just give me the next available thread ID. The reason I say it's finicky is this is a uint32.0, but and that specifically tells it to use the next thread ID available. The parameter will accept an integer, and if you give it an integer, it will set it to that thread ID. So if you put 0 in there instead of doing a uint, it will write the thread to the overwrite 0 thread ID, which is the first one, which is always your own process's thread ID. So if you do that, process will immediately crash. And when we get into the demo, I'll kind of show you how to actually do that and make sure that that's a uint, similar to what we did earlier. Last one is really easy. This is the first one we did when I was showing you guys TechNet. So because threads happen independently of our process, we end up with a problem. So that thread will start running our shellcode. But what happens to the memory when a process finishes? Does anyone know what the last thing that happens when a program exits? Yep, it frees. It frees the memory. So we have a thread running that we need to keep running because in our case, we're just doing a pop calc. So as soon as calc pops up, it's done, we're good. But in a real world scenario where you're doing exploitation, you're going to be deploying a rat, and you need that to continue to run. What this wait for single object API does is it allows us to say that, hey, don't move on until this thread completes. So it requires a handle, which is actually the output of create thread. So when you do create thread, if it's successful, it'll give you a handle. A handle is just a special kind of pointer. Pointers generally point to memory space. A handle points specifically to a process memory space. So you can just think of a handle as a pointer to a thread. So we give it the first parameter, which is a handle, and then we tell it, we give it an unsigned integer, and it's kind of like the mem commit and all that stuff, that there's a bunch of codes that mean different things. And this, almost always in malware scenario, you're only going to use one, and it's 0xf times 6. You want that tells it to wait infinitely. Just wait till it gets done. And I did, like I said, the slides are in the repo. I put the links to all the TechNets into these so you guys could refer to them easily. So again, that's why I call this 4.5, is because the only reason we're using this is because we're using create thread. If we were to use a different execution method, and there are a lot of them, and people are finding new ones every day, because generally by the time one gets published, EDR vendors start hooking that API and making it very hard to call. And there are some really fun, very creative ways to do it. There's one of my favorites right now is there's something called a fiber, which is a group of threads that can happen. It's basically you tell the OS, hey, I want this to happen. I don't really care when. It just needs to happen by this time. And it's so it's like a low priority thread. But because create thread is hooked by every EDR and AV, or create threads calls are signatured by AV, it gives us a different way to do the exact same thing, but different enough that it breaks the signatures. All right, I'm gonna go back into the Visual Studio here for a sec. And we're getting real close to being done. I know we're, so I just want to make sure, let's see, let's go. There we go. All right. So when we went back over to the slides a minute ago, we'd already called our shellcode, our memory allocation. We've copied our shellcode into it. So now we just need to start the create thread. And I'm gonna, as soon as I can find my damn point, I need to like, come on. There it is. All right. Give. What is it? Shift Enter? Sorry, I keep losing my pointer inside my VM. There we go. All right. Let's do. Again, I'm just going to copy these ones and talk through them. It's a lot easier that way and saves us some time. All right. So again, just like before, I put my syntax in here, so I knew it would be easy. I'm going to paste this in. One thing I didn't mention on the slide that I do want to mention now. So the first one all has all of the parameters, what we call in parameters. They're parameters that the function is going to do something with. Create thread is actually, if you look at the syntax here, we actually have both in, and if you don't see in and out both in here, you can assume they're all ins. But we also have an out parameter, and so what an out parameter does is kind of exactly what you would expect. The out parameter controls the output of the API call. So again, I told you before, we're going to use a lot of zeros in this API call. So you still got to look at what your expected type is. So our first one is expecting a pointer, so we're going to say 0. Again, we're gonna call 0. Here's our allocated memory from earlier, when we did virtual alloc and then we copied into it. We're going to use that same one again because it's still a pointer to our shellcode. We're going to zero out the parameter and the creation flags, and then up here, remember I saw the last one, it's finicky about making sure it's a uint versus an int, otherwise you'll end up overwriting your own thing. So to prevent that from happening, I just declared that above. I just declared a uint32, declared it as 0, and then I will call that by name down here. That means even if I was to sit there and type that in as uint32, there is a chance that it will get interpreted as an integer. Don't ask, I definitely haven't spent hours debugging code because for some reason the compiler didn't want to read my typing in the API call. So just as a word of warning, if you have the option to do an int or another type and you're using 0, it is always best to declare that as a variable and call it by the variable. That just guarantees that you'll get the right type. And then the wait for single object is stupid easy. Again, where up here we put, because this is outputting a pointer or a handle, we declared a variable when we called this, so it'll get saved to that. And then we're just going to feed that variable to wait for single object, and then we're going to tell it to wait infinitely. So minus that, that's about, minus all the comments in here, that's about 20 to 30 lines of code. That's a fully functional shellcode runner. Well, except for the shellcode. We haven't put the shellcode in yet, which we'll do in a sec. But that is all of the actual application logic to execute shellcode. They get a lot harder when you're using more advanced techniques, but like I said, all of that's just evasion. All right, I want to go back and I want to show you guys one more thing, and then we're going to open the floor for questions. All right. All right, So shellcode storage. I'm going to show you guys a really simple way to store your shellcode. This is a terrible, terrible idea. Don't do this if you're ever trying to stay hidden. It's great for demo purposes. It's great for like quickly, I want to test my AV and see how it detects and see what comes up in the logs or whatever. It's terrible for OPSEC. The shellcode is the most sensitive part of your loader. The shellcode is generally generated by a C2 platform, and every EDR vendor owns a copy of it if it's paid. If it's open source, even better. They've dumped all those shellcodes and they've written all kinds of signatures for looking for different byte sequences. If you put raw shellcode in your loader, it's gonna get caught. We are gonna do that because it's easy. The plan is in the future we'll build off of this. We'll take the simple loader and we'll learn how to make it more evasive. But I did want to point out though there are other ways to do this. You can save it in a resource file. I think some of the most popular ways I see right now is actually people hosting their shellcode on a remote server and having the loader application just go grab it in real time, like one line at a time, and break it up into small chunks. But the big thing is whenever you're doing, however you get your shellcode in here, make sure your shellcode is encrypted. It does involve you need to write a decryption part into your loader, but if you don't, if you do that, it doesn't matter how evasive you are. If you load raw shellcode into your process space, you're going to get owned by EDR. So the way we do this in C#, when we get our shellcode out of something, we get a string representation of that shellcode. And it's usually going to look something like, it's usually going to look something like 0x and then a couple of hex characters, like 0x, 0a or something like that. That's a byte represented in a string. It makes our brains able to understand it, but it's not how computers get it. In C#, it is a very specific format, which is it's 0 lowercase x followed by the 2 hexadecimal characters. Thankfully, you don't actually have to do this conversion very often because most C2 platforms, if you're deploying a RAT, will allow you to tell it what code format you want the shellcode in. Like MSF Venom, you have the dash format thing, and you just put dash format C# and it'll spit out the whole array for you. If you do, though, I did want to make sure you guys knew what the representation looked like, because there are some even paid ones that won't put it out in anything but C format. So you might have to do some go into Notepad and do some find and replace to fix it up. Which we're going to go back to our guy up here. And so earlier we declared our byte array with shellcode bytes. So inside of both of the other projects, there is a small shellcode. Word of warning, you probably shouldn't run shellcode that's been given to you by a hacker. I will tell you this shellcode is just generated from MSF Venom, but I could be lying. Don't run shellcode you find on ExploitDB. Trust me, that's a terrible, terrible idea. We kind of have sick, twisted sense of humors as hackers and love to do shit like, have it reach out to an IRC channel and post your IP address and all the information I can gather from your computer and talk about what a freaking idiot you are. I caught myself. So what I did do here is in the actual comment, I put the entire command that you need to generate the same shellcode. You do have to have MSF Venom installed in order to do that, but that will generate this same shellcode. So if you just want to go check to make sure I'm not lying, you're welcome to do that. This also brings up a very interesting point that I will bring when you're generating shellcode from C2 platforms. Every language has certain characters that mean special things. So in this case, you'll see that I have this -B and these 3 characters that are marked in -B in the MSF Venom generation. So 0x00 means one thing in all of machine code. It means stop. It means terminate. We call it a null terminator. If you have a 0x00 anywhere in your shellcode and you try to execute it, when the OS reads it, it's going to think that the shellcode's done when it sees that. So you need to make sure that none of those characters are generated to be 0x00. 0x0a is pretty much the same thing. It's just a new line, essentially, character. And 0x0d does something else special that I can't remember. Bottom line is you don't want those characters in there. So whenever you're generating, if most of them will have an option that say, hey, don't use these characters, make sure you have those in. That's true across pretty much all Windows devices. You need to make sure those characters aren't in your shellcode. So I'm going to copy this in since we've already actually, come on, there we go.
What's in there right now won't work, right? You're missing the front zero off of everything, every line.
No, it was just,
That's hidden. Okay.
yeah.
I was like,
I did test this. I thought you were asking me something else, but. All right, so I'm just going to copy this from this guy, and I'm going to. So when we declared our byte array, we added these two bracket braces here. So I'm just going to make this formatted a little better, so easier to paste in. But all we got to do is inside those brackets is copy that long string. And I still have an error. Where do I have an error? Expected. All right. Oh. All right. Remember earlier I talked about don't be dumb and forget about putting your semicolons? Yeah. Oops. All right. All right, we got no errors in our compiler. So now we should be able to compile this and execute it. So quick note, by default, Visual Studio will put will always default to execute or to compiling and debug. If you do that, you will put a bunch of extra symbols in your code, and it may or may not run correctly when you try to put it on a machine that's not where it was compiled. So you want before you compile any type of payload loader or anything like that, you want to go up here into this release. It normally will be put at debug, and you just want to swap that to release before you compile. So this project, because we have multiple projects inside the solution, we're going to right-click the Krabby Patty demo, and then we're going to click Build. And if the demo guides don't hate me today, it will compile. Hey, it compiled. All right, so now if we go to this location that is conveniently given to us, now the real test of the demo guides. Let's minimize. Let's go to Krabby Patty demo and go into the bin folder. Whenever you compile, it will create a bin folder inside of your repo. Then you can go to release. Did it pop calc?
I flipped mine to something else just to validate.
Oh, okay. Yeah, we'll find out.
But
So,
I had to turn off Defender, so it immediately erased it.
and the program pops up, it executes, and it popped out. If you guys noticed there, do you see how that black window stayed up for a few seconds? That is specifically because we did that wait for single object. That's something to be aware of when you're working with shellcode, is what API calls you're using versus what you're trying to accomplish. Because that's fine in a pop calc. It was up there for 2 seconds. Most users aren't going to notice that. But if you're running a rat and that box just lays there forever, you might want to think of another way, which, adding in something like telling the program when it launches to hide the window or something. But that in a nutshell is just how is writing just simple loaders. So I'm going to go back to slides for just a second.
Don't forget that real-time protection likes to be a pain and turn itself back on automatically.
Well, if you followed my instructions and created an exclusion folder, you wouldn't have to mess with it.
Yeah, I'm lazy.
That's true. That's the real answer. Because also, if you turn off, if you turn off the automatic submissions inside the actual Defender console, if you don't go change the registry, it still submits crap. Doesn't even turn it back on. It says it's off, but it still submits stuff, which is awesome to find out the hard way. There we go. All right. Yeah, it is ridiculous to try to, and Defender, or even paid Defender for Endpoint or whatever, is actually one of the easier ones to do. Like trying to do that in against, say, CrowdStrike or Set1, they actually don't function correctly if you isolate them from the network, because it basically, the way that those things operate is that if it's never seen something before, it sends it up to the cloud to do some machine learning scanning on it. Well, if you block that off, it's like, okay, I can't detect it. All right, I got my slides back here. So I just want to do a quick recap of kind of what our loader did. So to start, we imported our hard-coded shellcode string into that byte array. Then we allocated memory equal to the size of that byte array with virtual alloc. We copied our shellcode with Marshall copy. We set our EIP to the beginning of the shellcode by creating a thread. And then we profited. And I'll open it up for questions. As to quote Cochise, questions, comments, manifestos. Yeah.
I'll hold those for the end.
Okay. Any questions from here in the room? Anyone still awake? I know talking through coding stuff can be a little dry.
So for a lot of the stuff that you're covering was pretty technical. For people that are just being exposed to this and don't have the foundation, are there any recommendations like where to start so that some of these terms that they may not have been familiar with, like MalDev Academy or anything like that out there?
So I can't recommend, thank you for asking that, because I can't recommend MalDev Academy enough. It's a little on the pricey side, but not from technical training side, but $500 for a lifetime subscription is a bit, can be a bit out of certain people's price range, but it is a true zero to hero course. And it is pretty fantastic, and they're constantly adding new techniques into it. I think there's been 26 new techniques published this year in MalDev Academy. So it's really good. Otherwise, the biggest thing is go learn programming, just how to do some simple projects. Go write an automation script in Python. There's Python's got some great resources like Code Academy that are free. Learning C#. There's not a lot of great free training for C#. And honestly, the only reason I use C# in this is because, one, I knew it was a language that we hadn't really talked a lot about here. It is the default language for Windows developers. And when you run a C# assembly, from a OPSEC perspective, C# looks very normal. C# assemblies are very normal in Windows to see executing. And from a tactical and operational perspective, C# assemblies can be jammed into memory and executed without ever dropping the binary. If you already have a certain amount of control over the box, even if it's a limited shell, you can use some simple PowerShell to jam that whole assembly into memory, execute it, and you'll never have it drop and hit disk. So there's some tactical advantages there too. Mostly that's more useful, less in shellcode running, but more when you're writing PostX tools. But I still find it, it's just one of those languages that once you start working with it, it makes it really easy to rapidly develop your own offensive tools or take other people's offensive tools. Go pull down the source code for any of the SpectreOps Ghost Pack stuff. Go grab seatbelt, pull the source code. Now, if you have a basic understanding of how C# works, you can go obfuscate that in a way that you're not going to hit all these signatures. But yeah, and honestly, like, I'm very much a learn by doing kind of guy. Is take something like this, go in, break it, try to figure out, try to debug it. Maybe go grab another shellcode runner from GitHub. You search shellcode runner, shellcode loader, put in the language of your choice, put GitHub in the search string. You'll get 100 hits. Go grab one, start picking that apart, figure out how to take this one and then figure out, earlier I talked about we're using read, write, execute memory. That is a huge red flag. Go in, do some Googling, figure out how, I said the name of the API call earlier, but if you can't remember it, figure out how do you change memory permissions after you allocate, and figure out how to allocate that with read, write, and then change it to execute read after you copy in there. That will make that loader beat Defender. And oftentimes that's the bar we have to face in the real world. I can't count how many times I see full-blown big enterprises who are like, we got Defender, it's enough, right?
But then you ran Who Am I?
I never ran Who Am I?
Good system.
Any other questions?
So I had two in chat.
Okay.
First one.
Right.
What permissions do you have, or are you typically looking for before you start loading your own shellcode?
What permissions am I looking for when I start loading?
Yeah, or what permissions should you have on a box before you start loading your shellcode?
Oh, yeah, that's a fair question. It's marked in all the loaders. Don't be evil. Don't execute. Don't load shellcode on a box that you don't have permission to do it on. It's a crime. It's not even a gray area at that point. Like, you can get away with running nmap against something and go, oh, I'm not really doing it. You run shellcode on a box, you just committed a felony. Don't do that unless it's either a box you own or a box that you have explicit, preferably written permission to do so. So something your lawyer can take to the courts and get you out of jail.
So this one's going to be a little more specific, also from Coach Eyes. How do you fight back against ASLR in this kind of a setup?
You don't. So long story short, so ASLR, for those of you guys who are a little newer to this, it's a security idea inside of, I know it's in Windows, but I think it's in most Linux distros now too. The idea is that every time the machine boots, it's going to all the random stuff that comes up inside of all those memory things that are being used by the OS are randomized, so you don't know where they are at. Because what it used to be is early like this, we're writing a loader to be able to get shellcode into an expected memory place. It used to be you just dump your shellcode into some process's memory space, and then you just call it by the actual physical address. But that changes every time you reboot now, so you can't really do that programmatically. We don't really worry about that in this kind of scenario because we're not calling anything directly. We never put in a memory address. The only pointers that we used came from inside of our own process, and that will, until that process closes, that pointer will be, because of the way we allocated that memory, will always be the same. So you don't actually have to worry about ASLR in this case.
One more out of chat. He's rephrasing his first question. So if I'm on a box because I got a call back from somewhere and I'm trying to pop some shellcode or to escalate, jump around, do whatever, what would I be looking for? Do I need to have something specific installed? If I see EDR running, do I just give up?
So I think he's trying to think like user permissions versus like administrative.
Yeah, integrity levels.
Oh, okay. So in Windows, when you execute an application, and this is an application, when you execute an application, even if it's executing shellcode, that will execute in the permission context you are currently in. So this will execute with low privs. You don't need any privileges. That box that I just had, I wasn't an admin when I popped that. Now, you won't gain any privileges from that. You'll still just be a user. But if you're using that to, say, drop a remote access tool, and then you say we're using something like inside that remote access tool to escalate privileges, you could use those newfound privileges to re-escalate your shellcode runner and get a new beacon back that is in that escalated context. But it will operate in the user context you're in. The biggest thing you just need to make sure is that you have you just basically need basic low privilege user permissions, because you need to be able to execute something. I still had to click on something or run a command from the command prompt to do that.
That looks like it from online.
All right. Anything else for Inside Close?
So off that, you just have to get them. So kind of piggybacking off that question, within your code, can you easily elevate and take control of the box regardless of whether it's just a basic local user or an admin user?
Can you write code to do it? Yes. I don't know that I would put that inside a loader, because generally, in order to do those type of things, you would have to. You're generally going to have to target a very specific vulnerable aspect of the box. And when you're executing loaders are usually meant for initial access. So I might, in this case, we made an XC, but I could have made that a DLL, and I could have shipped that and named it into something that gets loaded by another process when just like we were loading kernel 32. Other processes loading things. If I could find a way to get that in the DLL search order above, it's a little beyond what we were talking about before, but a way to get that to load before the real DLL gets loaded, it's called DLL sideloading. That I could cause that to escalate. As far as writing that, generally you would write a separate piece of software to escalate, and then use that to call your original shellcode runner. At least that's how I've seen it operated in, and how I usually operate. All right. Cool. Thank you guys very much. I actually do have one question for you guys. First off, hopefully you guys found this at least somewhat interesting. I know it's a little bit dry content. Would you guys be interested in me taking this further and doing talking about like some like how we can make this a little more evasive and a little less? Is that something that you guys feel? Okay, cool.
I think it'd be good if you had like a scenario, like this is your objective, and then take you through the story of here's how we're going to get to whatever that is.
Maybe. That's a lot of work. Writing a lot of practical CTF type stuff for internal, that's a lot of work. All right, cool. I think we're good.
It's time to say goodbye. Goodbye. say